Hey everybody. Today we will be proving why our ANOVA assumption about the normality of the residuals implies the normality of the response, and in turn, any contrast. Let's begin. Let's write our theorem explicitly. If we assume our residuals in our model are normally distributed, then our response variable is normally distributed. Thus, also any contrast is normally distributed. And here is just the effects model of the ANOVA, where epsilon represents our residuals, and it is normally distributed with a mean of 0 and a variance. Alright, to first prove our theorem, we need to first prove some lemmas. If x is normally distributed with a mean of a and a variance of b, and c is a constant, then c plus x is normally distributed with a mean of a plus c and a variance of b. Alright, just as a reminder, let's write out the CDF of x. As you can see, that's just a clear integral that represents the normal distribution CDF. Alright, so let's write out the CDF of c plus x. Well, we can just use some algebra to rewrite it as the CDF of x. Let's subtract both sides with c. And now it's a CDF in terms of x. Alright, let's write that out as an integral. And so now it's just an integral from negative infinity to x minus c. Alright, let's just do some u sub. Here, we'll just say u is equal to x minus c. And now t is u minus c in that fraction. And recall that the derivative of u minus c, where c is just a constant, is just u. Alright, and now we can just rewrite negative c minus a as minus parentheses a plus c. And it's clear we have the normal CDF, where the mean is a plus c. Thus, c plus x is normally distributed with the mean of a plus c and a variance of b. Alright, here's our second lemma. If x is normally distributed with the mean of a and a variance of b, and c is a constant, then c times x is normally distributed with the mean of c times a and a variance of c squared times b. Alright, here's the CDF of c times x. And using algebra again, we can just divide both sides by c. And now we have a CDF in terms of x. And we know that, that's just a normal CDF. And we take it from negative infinity to x divided by c. Alright, let's do u sub again. Here, u sub will be u equals x divided by c. And recall the derivative of u divided by c, where c is just a constant, is 1 over c. Alright, well, 1 over c times our fraction, 1 over square root 2 times b times pi. And if we just want to move the c to this inside the square root, will just be 2 times c squared times b times pi. Okay. And recall, c squared over c squared is just 1. And we can multiply that to inside the exponent. And so that way, now u divided by c minus a becomes u minus c times a. And the bottom 2 times b equals 2 times c squared times b. Alright, well it's clear again that this is just the normal CDF. And the mean is c times x, and the variance is c squared times b. Thus, c times x is just normally distributed by c times x as its mean, and c squared times b as the variance. Alright, let's put things together. So the effects model for ANOVA is just y i's of j equal mu plus tau I plus epsilon i's of j, where mu is the grand mean, tau I is the effect of the ith group, and epsilon is i's of j is the residual of the ith group and the jth member in that group. Alright, recall that mu and tau I are not random variables as we have a fixed effects model, as they are calculated from the data we collect. Thus, mu plus tau I is a constant. And since we assume epsilon, our residuals, are normally distributed with the mean of 0 and a variance, well then y i's of j, our response variable, is normally distributed by a mean of mu plus tau I and a variance. Alright, let's do this for contrast now. So let's recall the definition of a contrast. It's a linear combination of population means, where it satisfies n of I times c of I equals 0, although we're not going to be really using that condition in our proof. And for the sake of the background knowledge in this class, we will assume without proof that the sum of normally distributed variables is normally distributed. Alright, let's start our proof. Well, since mu is the sum of y divided by n, and we've concluded that y is normally distributed when our residuals are normally distributed, then the sum of y is normally distributed because we have already assumed the sum of normal variables is normal. Alright. And from our second lemma, we proved that a constant multiplied with a normally distributed variable is normal. Well, mu is just the sum of y times a constant, that constant being 1 over n. So mu is normally distributed. Alright, well, so our contrast is the sum of normally distributed variables. those variables being mu of I, and those constants, and each of those are being multiplied by a constant. Well, again, once again, using our first assumption that the sum of normal variables is normal, and our second lemma that a constant multiplied with a normally distributed variable is normal, then it's simple to see that our contrast is normal. Thus, our assumption of the normality of residuals implied that the contrasts are also normal. And since main effects and interaction effects are contrast, then they also are normal. Alright, well thanks everybody. I hope my explanation was able to be clear enough for you to understand why our ANOVA assumption that the errors are normally distributed in turn implies that a response variable and in turn any contrast is also normally distributed. Thank you.